And Christine, you're right about that. That watch is a very big, important thing here. It is already underway, but I'll tell you, at this hour, it's strange here, almost eerie. There is no rain, there is no wind, absolutely quiet, but most here along the coast and the low-lying areas know what's coming.
A startling revelation recently shook the scientific and emergency response communities across California as geologists announced a red alert, triggered by the discovery of mysterious fluid pathways deep beneath several major fault zones. These findings have not only escalated concerns about seismic activity in the region, but have also introduced new variables to a landscape already brimming with geological complexity. The alert is not simply precautionary. It is based on concrete, data-driven observations that indicate unusual subterranean movement of fluids, specifically in zones historically associated with significant earthquakes. Before we start, smash the like and subscribe buttons for more updates. The focal point of this discovery lies in the detection of anomalous fluid migration patterns detected through deep Earth imaging technologies such as magnetotellurics and seismic tomography. These methods allow geophysicists to visualize the movement of electrically conductive materials beneath the Earth's crust. In recent weeks, these technologies have captured unsettling images of fluid intrusions at depths ranging from 10 to 20 kilometers, precisely where tectonic stress accumulates before rupture. What has particularly drawn attention is the speed and directionality of these fluids, which appear to be pressurizing segments of faults that have already been flagged as overdue for seismic release. California's San Andreas fault system, one of the most monitored and studied fault lines in the world, is now under intensified scrutiny. Geologists observed that the newly discovered fluid pathways intersect with locked segments of the San Andreas, Hayward, and Garlock faults, areas that have not released significant energy in decades. The concern stems from the fact that these fluids can reduce friction along fault lines, acting as a lubricant that can trigger sudden fault slippage. The presence of high-pressure fluids along locked faults has long been a red flag for imminent seismic activity, and the evidence surfacing now fits that dangerous profile. Scientists from leading institutions have been poring over real-time data collected from borehole sensors, GPS arrays, and satellite interferometry. One alarming feature of the data is the correlation between microseismicity, small tremors that often precede larger quakes, and the advancing fluid fronts. These tremors have become increasingly frequent and are now being reported in clusters around zones where fluid movement has intensified. The pattern resembles what was observed prior to the Ridgecrest earthquake in 2019, albeit with even more pronounced fluid involvement this time. This phenomenon is not just limited to increased microseismicity. There is evidence suggesting that the fluid pathways are altering the mechanical properties of the crust. Measurements show changes in the poroelastic behavior of rocks, how they deform under stress when saturated with fluid. Such changes can destabilize fault zones, making them more susceptible to slippage. These fluids, which may originate from deep within the Earth's mantle or from hydrothermal sources, could be mixing with existing mineral compositions, thereby weakening structural integrity in unpredictable ways. The Red Alert declaration stems from the convergence of several risk factors. First, there is the fluid movement itself, which is unusual in both volume and rate. Second, the precise locations where these fluids are surfacing align almost too perfectly with high-risk fault segments. Third, the broader geological context includes a dry year with reduced groundwater levels, which historically correlates with increased tectonic sensitivity. The weight of missing water has long been theorized to affect stress distribution underground. With reservoirs and aquifers lower than usual, the redistribution of crustal stress may be amplifying the destabilizing effects of these fluids. These subterranean developments pose a multifaceted threat. Urban centers like Los Angeles, San Francisco, and Bakersfield sit atop or adjacent to these fluid-prone fault lines. A sudden release of seismic energy in these areas could devastate infrastructure, cripple utilities, and lead to catastrophic human loss. The geological implications are just as profound. If these fluid paths continue to expand or pressure upfaulted rock segments, it could signify the onset of a seismic swarm or even a cascading series of large magnitude earthquakes. The interconnected nature of California's fault systems means that a rupture in one area can trigger movement in adjacent regions, a domino effect that geologists have warned about for years. understanding the origin of the fluids has become a top priority. While some theories suggest deep magmatic sources, others posit that the fluids are remnants of ancient subduction zones, long buried and only now reactivated due to changing stress regimes. Still others believe that human activity, such as fracking or deep well injection, could be exacerbating natural pathways, although no definitive evidence currently supports that link in this instance. Regardless of their origin, the presence of these fluids signifies a dynamic and evolving subterranean landscape that challenges traditional models of earthquake forecasting. The implications for predictive modeling are substantial. Traditional earthquake forecasting has relied heavily on historical seismicity, GPS data, and crustal deformation rates. The new data introduces a volatile, less predictable element, fluid-induced stress changes, which can fluctuate rapidly and influence fault behavior in non-linear ways. Geophysicists are racing to incorporate these variables into simulation models, hoping to refine short-term forecasting methods. Machine learning algorithms are also being trained on this expanding dataset, with the aim of detecting subtle precursors that human analysts might miss. Public safety agencies are not taking the alert lightly. Emergency management teams have activated higher readiness levels, stockpiled supplies, and begun simulations for worst-case scenarios. Urban planners and civil engineers are revisiting retrofitting priorities, particularly for hospitals, schools, and bridges located near the identified high-risk fault zones. Early warning systems are being recalibrated to prioritize data from sensors monitoring fluid movement. Rather than relying solely on tectonic strain indicators, this holistic approach could buy critical seconds or even minutes of warning in the event of an actual rupture, time that could save lives. The alert also raises ethical and logistical questions about communication and preparedness. How do you alert millions of people to an invisible and complex threat without inciting panic? How do you balance transparency with the inherent uncertainties of geological forecasting? State officials are coordinating with scientific bodies to craft messaging that is clear, actionable, and rooted in evidence without overstating the immediacy of danger. It's a delicate balance, and one that is being tested in real time. Meanwhile, researchers are deploying additional instrumentation to better map the subsurface fluid networks. Autonomous drones equipped with ground-penetrating radar and magnetometers are being flown over rugged terrain to collect high-resolution data. Deep Earth observatories are ramping up data acquisition. And even fiber optic cables buried underground are being repurposed to act as seismic sensors using distributed acoustic sensing technology. The goal is to create a three-dimensional, time-evolving map of fluid movement that can be cross-referenced with tectonic activity and rock deformation patterns. This unfolding situation has also drawn international attention. Geological organizations from Japan, Italy, and Chile, countries with their own seismic histories, are collaborating with US researchers to share data and models. These partnerships aim to better understand how fluid dynamics influence fault stability globally, not just in California. There's an emerging consensus that the Earth's crust is far more fluid sensitive than previously believed, and that subterranean fluids may play a key role in both triggering and inhibiting earthquakes. Beyond the immediate threat, this discovery challenges long-held geological assumptions. It suggests that fluid pressure, not just tectonic strain, can be a primary driver of seismic events. It implies that the Earth's interior is not a passive recipient of stress, but an active participant in redistributing that stress through complex hydraulic systems. The red alert in California may thus be a harbinger of a new paradigm in earthquake science, one where fluid dynamics and tectonics are viewed as two intertwined forces, constantly reshaping the crust. For residents of California, the implications are sobering. Living atop some of the world's most active fault lines has always carried risk, but this new layer of complexity adds urgency to preparedness efforts. Earthquake kits, emergency drills, and structural reinforcements take on renewed significance when the ground beneath one's feet is not just shifting, but now potentially being destabilized from below by pressurized fluids. The challenge is to stay informed, prepared, and engaged without succumbing to fear, a balancing act that will define California's resilience in the face of this looming geological uncertainty. The scientific community, for its part, is approaching this situation with a mixture of caution and determination. Every data point, every sensor reading, and every tremor is being scrutinized for clues. There is a sense that the Earth is trying to communicate, using a language written in pressure gradients and microfractures. Interpreting that language in time could be the key to mitigating disaster. The red alert is not just a warning, it's a call to action for researchers, policymakers, and the public alike to recognize the hidden forces shaping the future of seismic risk in California. New drilling missions are being considered to collect rock and fluid samples directly from the zones of interest. Such samples could offer invaluable insights into the chemistry, temperature, and pressure conditions driving the fluid migration. Laboratory experiments will then attempt to replicate these conditions to better understand how faults might respond to similar stimuli. This research will take time, but its results could redefine how we assess and manage seismic risk in fluid-rich geological settings. Furthermore, the environmental implications of these fluids must not be overlooked. If they rise close to the surface, they could interact with groundwater systems, potentially contaminating them or altering their chemistry. This raises additional concerns for agriculture, drinking water supplies, and ecological balance in regions already stressed by drought and climate change. Monitoring stations are now being fitted with sensors to detect chemical anomalies in wells and springs, offering another layer of data to assess the scope and impact of this subterranean phenomenon. As scientists continue to piece together this intricate puzzle, one thing is clear: the Earth beneath California is far from static. It breathes, shifts, and now it appears, flows. The red alert is not a moment of panic, but a moment of profound recognition that even the most familiar landscapes conceal mysteries that can reshape lives and rewrite scientific doctrine. The ground may seem solid, but in truth, it is part of a living, dynamic system whose currents run far deeper than the eye can see. California now stands at a crossroads between vigilance and vulnerability. The discovery of these mysterious fluid pathways has shifted the conversation from if to when, and the red alert serves as both a warning and a catalyst. It has galvanized scientific inquiry, spurred emergency preparation, and reminded millions that beneath the surface, the Earth holds secrets that can change everything. The next steps, measured, scientific, and prepared, will determine not only how the state responds to this evolving threat, but how it redefines its relationship with the powerful forces below. This evolving geological drama continues to unravel deeper layers of complexity as scientists, policymakers, and communities grapple with the ramifications of the red alert. As more information surfaces about the unusual subterranean fluid movements, a picture emerges not just of impending seismic danger, but of a vast, dynamic system whose influences extend well beyond earthquake mechanics. The implications reach into technology, infrastructure resilience, resource management, and even the future of urban planning across the seismically volatile regions of California. One immediate area now under intense investigation is the interaction between these fluid pathways and geothermal energy systems. California is home to numerous geothermal plants that harness the Earth's internal heat through networks of boreholes and fluid circulation. These operations are, by their very nature, intertwined with the subsurface hydrology and fault systems. Scientists are now exploring whether the expanding fluid channels are in any way connected to regions of geothermal activity, and whether such connections might amplify risks or, conversely, present opportunities for better energy extraction and monitoring. Geothermal reservoirs, especially those near fault intersections, could be sensitive to shifts in fluid dynamics. Any abrupt change in pressure distribution might not only impact energy output, but also the structural integrity of the faults themselves. In places like the geysers or the COSO geothermal fields, researchers are intensifying monitoring efforts to determine whether the anomalous fluid activity overlaps with or affects existing geothermal systems. The unexpected coupling between these energy operations and newly discovered fluid conduits introduces a new layer of responsibility in energy management, demanding that operators proceed with heightened vigilance. Beyond energy, the implications for advanced infrastructure monitoring are becoming increasingly apparent. California has already led in implementing smart sensor networks embedded in bridges, tunnels, and high-rise buildings to detect structural strain during seismic events. However, these systems were designed primarily to respond to earthquakes, not to predict them based on underground fluid dynamics. Now, the urgency to upgrade sensor algorithms to include fluid pressure data has taken center stage. The incorporation of hydrological stress markers into early warning frameworks will likely revolutionize the way infrastructure systems communicate with one another. Imagine a near-future scenario in which a deep-buried pressure sensor near a fault detects an acceleration in fluid migration. That data could automatically trigger preemptive protocols, halting train operations, shutting down vulnerable pipelines, or adjusting dam flow rates, all before a tremor occurs. This level of responsiveness demands not only technical innovation, but also cross-disciplinary collaboration between seismologists, hydrologists, engineers, and emergency planners. The financial implications are significant. As insurers and reinsurers analyze the mounting evidence of subterranean instability, they may reevaluate risk models for regions built on or near the affected faults. Premiums could shift, coverage policies might tighten, and some areas may become prohibitively expensive to insure altogether. The red alert has thus rippled into the financial sector, where actuaries and risk assessors are incorporating fluid migration data into algorithms traditionally reliant on surface-level factors and historical earthquake frequency alone. This reevaluation of risk brings urban development practices into question as well. California, despite its seismic history, has continued to expand into areas once considered marginally at risk. With this new data, planners may need to reconsider zoning policies altogether. Real estate developers could face more stringent geological surveys, while already built areas near expanding fluid zones may require retrofitting mandates far beyond current building codes. This introduces a tension between economic growth and geological caution, a tension that now finds itself under the microscope as the red alert continues. Educational institutions, particularly those with geology, civil engineering, and environmental science programs, are also pivoting rapidly. The sudden prominence of fluid-induced seismicity is reshaping curricula and research priorities. New courses are emerging that focus specifically on crustal fluid mechanics, fault hydrodynamics, and seismic modeling under fluid pressure gradients. Graduate students and postdoctoral researchers are seizing the opportunity to explore previously niche fields that now sit at the forefront of global concern. This academic surge is being mirrored in public science communication. Museums, science centers, and even public libraries are organizing informational sessions aimed at helping Californians understand the science behind the red alert. Virtual reality simulations now allow people to visualize what fluid movement beneath their homes might look like, driving home the idea that the Earth's interior is a dynamic living system. These tools serve not just to educate, but to psychologically prepare communities for a future where seismic activity could arrive not just as a bolt from the blue, but as a gradually mounting phenomenon visible in data, if one knows where to look. Meanwhile, ecological consequences are also being brought into the discussion. As subsurface fluids migrate, they may influence the thermal regimes and chemical composition of aquifers, which in turn can affect surface ecosystems. In arid regions, where water sources or mineral availability, factors that directly impact agriculture. California, a global agricultural powerhouse, must now consider whether crop yields could be affected not just by drought or pests, but by hidden changes in the ground's chemical composition. Agricultural scientists are launching new research efforts to monitor soil samples from farms situated over known fluid pathways. There's another dimension to this crisis that involves data security and technological infrastructure. Much of California's high-tech industry, including server farms, data centers, and telecommunications hubs, rests on seismically sensitive ground. With the emerging possibility of fluid-induced fault activation, tech companies are reassessing the stability of their physical assets. Backup systems, redundancy protocols, and even the locations of new data facilities are being reconsidered in light of the growing subterranean threat. A burgeoning field of interest is now looking into whether artificial intelligence and big data analytics can be used not only to predict seismic events, but to anticipate fluid behavior deep within the Earth. These tools, powered by vast data sets from sensors, satellite imagery, and laboratory simulations, are enabling a level of prediction once thought impossible. AI is being tasked with identifying subtle correlations between fluid pressure fluctuations and microseismic activity, potentially offering a roadmap to more accurate short-term forecasting. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on mysterious fluid paths? Will California face a major quake? We want to hear from you. Thank you for watching and see you next time.